last class, we left off talking about a bunch of laws. Everyone loves laws. We talked about the law of definite proportions, the law of multiple proportions, the law of conservation of mass, and these were all working towards one big idea. And that one big idea was atomic theory that John Dalton explained in 1808. So he explained those three laws that we were talking about with the atomic theory that has these points as follows. First point, each element, anything that's on our periodic table, as we know it today, as they knew it then, they're different, contains tiny indestructible particles called atoms. That's the smallest piece of an element, which is true. All atoms of a given element, so any element, pick any element you want up here, they're going to have the same mass and other properties that make them different from other elements. Also, atoms combine in simple whole number ratios to form compounds. This one arises out of the fact that they're indestructible. You can't have half of an atom because you can't break them into pieces. It's no longer that element, it's no longer that atom. And those form compounds. We'll learn some names for compounds next chapter. Atoms of one element, so pick any element on here, they can't change into atoms of another element. Once you're one element, you're stuck. That's it. You're that element. In a chemical reaction, atoms change the ways that they're bound together. So the connections between the atoms can change, but the atoms themselves stay being the same atoms, the same elements. And we've got a lot of evidence for atoms today. People can even do fun things like push them around and take pictures of them to make stop motion videos with atoms. So that's our atomic theory. We'll cover some more history. So that's Dalton. Thomson came along a bit later and constructed a partially evacuated, partially vacuumed glass tube. So low pressure in this glass tube, kind of like our modern incandescent light bulbs. He called it a cathode ray tube. It sounds really cool. Sounds like a Bond villain sort of thing to make. He took a high voltage of electricity and applied it between the electrodes at the end of the tube. This is kind of what the tube looked like. There's a cathode and an anode. And noticed in this glass tube a beam of particles. He called the beam of particles cathode rays. They traveled from the negatively charged electrode to the positively charged electrode. So that's some cool observations. Thomson found that those particles that compose the cathode ray have the following properties. They travel in straight lines. So they're just one straight line. They're independent of the composition of the material from which they originate. So you can use anything for your cathode. Any material can make cathode rays. It wasn't like one particular special thing. He could use different things for his cathode. And they carry a negative electrical charge, which is why they were traveling from the negative side. They're getting repulsed by the negative side and being drawn towards the positive side. Just like the way that magnets attract and repel. So some properties of electrical charge, because we're going to be talking about some small particles that have electrical charge. If you've got something that's positive and something that's negative, those will attract each other. Opposites attract. This is true for subatomic particles. If you have two positive charges, the positive charges will repel each other. If you have two negative charges, the negative charges will repel each other. So like charges repel, opposites attract. If you add a positive and a negative charge together, you get a zero charge. So the positive and negative charges are equal and opposite. don't know what I was writing there, opposite. So the positive has the same strength as the negative, it's just that they're opposite charges. It's not like the positive is like 1.5 times the negative, they're equal strength, just opposites. Using some fancy experimentation, Thomson deflected cathode ray particles using electric and magnetic fields. So he has this cathode ray beam, that would send undeflected electron particles right down the middle of this horn. And using some positive and negative charges, he was able to deflect them off to the side. And using some fancy physics, you could figure out how far they were deflected. You could measure how far they were deflected and correlate that with the mass of the particle related to the charge. So we measured a value, a charge to mass ratio of this many coulombs, which is a unit of charge, per gram. So if you had a gram of electrons or a gram of these cathode ray particles, then it would be this many coulombs of charge. One of the implications of this is that the cathode ray particle was about 2,000 times lighter, or 1/2000th of the mass of hydrogen, which is the lightest known atom. This means that the cathode ray particle is smaller than a hydrogen atom. And we see that it's an electron just in the next slide, so I'm just going to write electron. So an electron is smaller than a hydrogen atom. And this kind of foils one of Dalton's points in his atomic theory. These smallest particles, these atoms, are not actually indestructible. They're not the smallest thing. They're made up of other things, and one of those things is electrons. So electrons are negatively charged, low mass particles, and they are in all atoms. So all atoms have electrons, which is kind of interesting. So this foils one of the points of Dalton's atomic theory. Didn't want to put that there. Moving on to another cool experiment, Millikan's oil drop. So a little bit later on, this is about 100 years out from Dalton's atomic theory, Robert Millikan performed the now famous oil drop experiment. So he took some oil and atomized it and sent it into this chamber up here, and some of the oil drops would make their way through a tiny little hole in the top in this positively charged plate, and there's a negatively charged plate on the bottom. And by introducing some ionizing radiation to hit the oil drops and using a light source and a viewing microscope, could tune the charge in this chamber and cause the oil drops to levitate in the middle. So he could figure out what the charge was on that oil drop, and then by looking at it through this viewing microscope and making some measurements, he was able to figure out the size of the oil drop and figure out the mass of the oil drop. Very clever experimentation. So by looking at strength of the electric field and figuring out the masses of the drops, Millikan was able to calculate the charge of each of those individual drops. So he did this repeatedly with different sized drops, just whatever floated down into his viewing microscope. And he observed that the charge was always a whole number multiple of negative 1.96 times 10 to the minus 19. And so that is the fundamental charge of a single electron. The reason it was always a whole number multiple is there were multiple extra electrons maybe on the oil drop. And so by measuring a bunch of different things, he was able to kind of law of multiple proportions his way down to figuring out what the charge of a single electron was. And since we had the mass to charge ratio from J.J. Thomson's cathode ray experiment, now we've got the charge. You could figure out the mass of a single electron. Very clever stuff. This is what people did without TV. And so this discovery of electrons led to more questions. If electrons are negatively charged, in order for them to stick around in atoms, there must be a positive charge to balance out that negative charge. So there's got to be a positive charge in the atom. Where do these opposite charges fit together? And so people came up with all these crazy ideas of what an atom might look like, how it might be structured. Because they didn't have the ability to actually look at them, you can't really magnify down that far. And so Thomson came up with the famous plum pudding model. So the idea that you've got a big glob, basically, of positive charge, and then within that, like little maybe raisins, within that there's raisins of negative charge electrons that are just kind of evenly dispersed in this plum pudding. We might call it a cookie dough model today. It's the raw cookie dough model, sort of what they were doing at the time. So Thomson proposed that negatively charged electrons were small particles and they were held in a positively charged sphere. Similar time frame, radioactivity was discovered. So radioactivity is the emission of small energetic particles from the core of certain unstable nuclei. You may remember from Chem 20. This was discovered by Henri Becquerel and Marie Curie. And when they discovered this, that you could create beams of these radioactive particles, this allowed them to probe or look at, investigate the structure of the atom. So there were three main types. We're not going to talk about them at length here, but they're alpha particles, beta particles, and gamma rays. And alpha particles primarily what they were using to probe the electrons. So they could direct beams of beams of alpha particles at something and just kind of see what happened. So that'll come up later. Maybe in Chem 2. I don't remember. Okay, so Rutherford in 1909 came along. He had worked with Thomson, and he did some experiments to try to see if Thomson was right. So he designed an experiment where he took positively charged alpha particles and directed them at a very, very thin sheet of gold foil. The idea was, if it's a very thin sheet of gold foil, maybe only a couple of atoms wide, you should be able to direct the alpha particles to just kind of crash through that thin foil. Since it's just kind of all plum pudding consistency, it might slow down, but you would expect that it would just mostly pass through. Kind of like if you were shooting BBs at like a piece of paper. You might expect that the air gun BBs would hit the paper and slow down a little bit, or cardboard or something, but they would go through and just kind of continue in a straight trajectory. So that's what he wanted to test. So this is what the experiment looked like, one conceptualization. So a lead block with an alpha particle source in the middle to direct this beam of alpha particles at the really thin gold foil. And what he saw was that most of the alpha particles passed through, pretty much just straight through like expected. However, some of them deflected off to the sides, some of them even deflected back, which was not at all what was expected. So these are incredibly unexpected results. 1 in 20,000 apparently bounced back. So if you shot an air gun, if you shot a BB gun at a piece of paper and the BB came back at you, I would be very alarmed. What's this paper made of? And that's sort of similar to what they were thinking at the time. So Rutherford's quoted as having said, about as credible as if you had fired a 15-inch shell at a piece of tissue paper and it came back and hit you. A 15-inch shell being like a 15-inch diameter thing you'd fire from a cannon. So Rutherford created a new model to explain his results. One thing that I want to talk about really quickly, this conceptualization that we have in this slide doesn't really completely represent, I think, how crazy of an experiment this was. So they didn't have like fancy detectors. It says detector here along the outside. This was just like a piece of material that would like light up when it was hit with one of these alpha particles. But they didn't have like an electronic machine to count all of those detections. Somebody sat in a dark room and just looked at basically a black screen for hours a day and manually recorded, yep, I saw one, there's two, there's three, there's four, manually recorded at each of these like different intervals around this screen. So that seems like a fun job, just sitting in the dark looking for little blinking lights. I wouldn't go crazy. So that's how they did that. So Rutherford, moving on, concluded that matter must not be this plum pudding model. It must not be this nice smooth consistency. In order for things to bounce back, they must have hit something hard. And so the nuclear model cropped up around this. There's a small, tightly packed, very dense nucleus that's got most of the matter of an atom or a particle. And then around that is just kind of a cloud of electrons. So some of the things were coming back, they were hitting the nucleus and then bouncing off at weird angles. So Rutherford proposed this nuclear theory. So in Rutherford's nuclear theory, most of the atom's mass, like 99% of the atom's mass, all of its positive charge are in the nucleus. So we've got positive charge and most of the mass. And then most of the volume of the atom is empty space. You've got the tiny little electrons kind of dispersed throughout. And then the number of negative charges equals number of positive charges. The positive charges being protons. So the number of electrons equals the number of protons. Questions so far? Lots of very riveting history. Some of it is actually cool, I think. All right. So Rutherford's model was really good, really successful, but they realized that it's not complete. For example, hydrogen contains 1 proton, helium contains 2 protons, but the mass of helium is 4 times that of hydrogen, not just twice the mass. So there's got to be something else going on. Later work by Rutherford and one of his students, James Chadwick, demonstrated that this was due to neutrons. So we've got a third subatomic particle entering the picture. Neutrons are neutral particles that also show up in the nucleus. So these have no electrical charge, unlike protons and electrons. And their mass is similar to protons. So mass of a neutron similar to that of a proton within like a thousandth or 2,000ths of their mass. So this would be like if you and another person were like 0.1 or 0.2 pounds different. That's sort of the similarity that we're talking about in terms of our protons and neutrons. Super similar. All right, so the hydrogen atom is just 1 proton. It doesn't have any neutrons typically. The helium atom is 4 times as massive because it has 2 protons and 2 neutrons. And neutrons are about the same size, same mass as protons. So the structure of the atom as we know it now is that we've got a very dense nucleus. So the nucleus is a little tiny cluster of protons and neutrons. and electrons fly around it. The electrons are really small in terms of their mass, but dispersed over an incredibly large area. So because of these atoms being mostly empty space, matter is actually a lot more just empty space than we would probably think it is. So if a nucleus is the size of a period, like maybe the period on the board, probably smaller than the period on the projector screen, then the electrons are going to be 10 meters or about 33 feet away. So the period, let's just go ahead and say that it's the one on the board. If that's our nucleus, then our electrons are like over here. And there's all this empty space in between. There's so much empty space that if you took a grain of sand and made it solid atomic nuclei, it would weigh 11 million pounds, which is a lot of weight. I don't have a good idea of what's a thing that weighs that much. I'm just going to skip that. Okay, subatomic particles. These are our three subatomic particles. We've got protons, neutrons, and electrons. Protons are positively charged. Neutrons are neutrally charged. Electrons are negatively charged. And we can see the mass difference for the proton and the neutron only shows up in this fourth decimal place, third decimal place. And it's not very much. And then the mass of the electron is times 10 to the minus 31. It's really, really small compared to our proton and our neutron. Our book likes this example of if the proton has the mass of a baseball, then the electron would have the mass of a grain of rice. There's a more upscaled version that I discovered. If the electron is instead of a grain of rice, if it's a watermelon, then the proton is a semi-truck. So I think that's a little bit more fun because they're big, and you can imagine them being very painful if they hit you. I wouldn't want to get hit by a watermelon, but I definitely wouldn't want to get hit by a semi-truck. Hopefully you don't either. So these units of kilograms are really unfortunate to work with because of scientific notation, and so instead we've got an atomic mass unit. So our atomic mass unit is more about the size of a proton or a neutron. It's defined as 1/12 of the mass of a carbon atom containing 6 protons and 6 neutrons. This is like normal carbon. So the proton and the neutron are about 1 AMU. Not exactly, but pretty close. More subatomic particles. Stuff. The charge of our proton and electron, we talked about this already. They're equal in magnitude, so in terms of their strength, they're equal, but they're opposite. So the proton's positive, the electron's negative, and they cancel each other out when you pair them together, and the neutron has no charge. Here's a table from our book. We've got our different particles, our proton, neutron, electron, their masses in kilograms, their masses in AMUs. We can see that proton's about 1, neutron's also about 1, and electron very small, about a 2,000th. Relative charge, our proton has the +1, our electron has the -1, and if we quantified it as coulombs instead of relative charge, these are the number values that go with them. We'll usually just talk about them in terms of the relative charge +1, -1. There might be a couple instances where the actual Coulomb charge comes into play. So matter is typically charge neutral because we've got equal numbers of protons and electrons present in matter. Normal atoms have the same number of positive and negative charge, so it's all equal, it's all good. However, you can get charge imbalances. Usually they can build up slowly. Usually they build up slowly. But then when they go to equalize, it's very sudden. So for example, static electricity shocks, like if you're shuffling your feet around the house, and you touch something metal or you bump into somebody and you get that, ow, a little shock. That's all of the charge normalizing itself kind of in one go. Lightning also being an example of this. It was actually raining and there was like lightning and thunder when I left my house today, which was interesting. I brought an umbrella and then I got here and it's perfectly clear skies, so that's cool. But lightning is the example of like lots and lots and lots and lots of charge imbalance building up and then equalizing in a short amount of time. Any questions so far? Cool. All right, we're going to talk about what the subatomic particles kind of do for our atoms, our elements. So the number of protons. Protons define the element. If an atom has one proton, that makes it hydrogen. If it has 2 protons, that makes it helium. If it has 10 protons, it's neon. If it has 18 protons, it's argon. It's solely based on the number of protons. So the number of protons that something has makes it that element. We also call this the atomic number, which has the symbol Z for Zahl, which means number in German. The reason that it's in German is because the Germans were really big on chemistry for a long time, and so they kind of like paved the path for chemistry, and so it got to be their language. And Z for Zahl for number. Our periodic table wasn't always arranged this way, and so it was just referring to like which number in the series you were talking about. So they just ordered them in terms of atomic number instead of laying them out with the periodic table that we have today. So Z is number of protons, P+. So if we look at a periodic table, we have, typically a periodic table is going to have these 3 things. It's probably going to have more as well. So we've got a chemical symbol. It's 1 or 2 letters. We've got our full name for our chemical symbol. Notice that it's not capitalized. And we've got an atomic number, Z, that's usually up in the top. In the one that we've got up next to me, it's in the top right corner. Usually there will also be a mass number in the bottom left corner. We just haven't gotten to that yet. And that information is there for all of the elements. So our elements have a unique atomic number ranging from 1 to 118. In our classroom, we've got an older periodic table, so it hasn't been named. It wasn't named when this one came out, so it's UUO, Ununoctium, or just 118 in whatever that would be called. Our chemical symbol is a 1 or 2 letter abbreviation. There's 2B is an abbreviation. The first letter is always capitalized. The second letter is always not capitalized, if there's a second letter. It's always lowercase. As you probably know, some of the chemical symbols are based on English names. Some of them are based on Latin names. So for example, Na for sodium comes from the Latin name natrium. And a lot of the world still uses some of the Latin names. So some of them, many of them don't intuitively make sense, and you kind of just have to memorize them. So that's number of protons. If we change the number of neutrons, if we adjust the number of neutrons, then we get what's called isotopes. So isotopes same element, but with a different mass. And so this is actually counter to Dalton's atomic theory. He said that they all had the same mass and the same properties, which we now know is not true. They have a different mass because of the different number of neutrons. So for example, neon atoms, because they're neon atoms, they have 10 protons. They're always going to have 10 protons if they're a neon atom. However, they could have 10, 11, or 12 neutrons. Those are all numbers that allegedly exist. You could probably have other higher numbers. You could probably have lower numbers. Not all numbers of neutrons are going to exist at any given time. And the relative amount of each of these isotopes in a naturally occurring sample is roughly constant. So if you go out in the world and you collect a sample of a particular element, typically you'll get about the same ratio of the different isotopes. One of them will be dominant, and the other ones will have some other amounts. And that's generally true wherever you go in the world. It's not always true, but generally true that you'll have the same natural abundance of isotopes. Now that we have neutrons on the board, we can also talk about A. So A stands for, well, we call it atom number, or mass number, sorry. Mass number is represented by the symbol A. It's the number of protons plus the number of neutrons, just the number of massive particles, the big ones, not including our electrons, that are in the nucleus. I think A stands for, I think this is how you spell it. It's German, Atomgewichte, or something like that. Atomic weight, I think, is like a rough translation. So that's what the A stands for. It actually stands for atomic weight, whereas Z was number. So the atomic weight of an element is mostly determined by its protons and its neutrons. And there's a bunch of ways that we can write out isotopes. One of those ways is with mass number on top, atomic number on the bottom, and then our chemical symbol big and in our normal writing place. So mass number, protons plus neutrons, our atomic number, just protons. There are a couple of ways that you can remember which one goes where. One of them, if you remember the symbols, A and Z, what comes first in the alphabet? A. A comes before Z, so we go from A up top to Z down below. You could also remember that the bigger number goes on top. The top number will at most be the same as the bottom number, just for hydrogen. Or we're also going to have neutrons, and so it'll be big number over little number. And then our symbol just being our chemical symbol. Another thing I'd like to point out is that the atomic number and the chemical symbol are linked. If you have one, you can get the other, because the number of protons, the atomic number Z, determines the element, which determines the symbol. You can work the other way as well. So if you have the symbol, you can find the atomic number. So those three isotopes of neon that we were talking about would be 20 over 10 Ne, 21 over 10 Ne, 22 over 10 Ne. There's other nomenclatures, other notations that we can use as well. So you can also have chemical symbol dash mass number or chemical name dash mass number. Other examples being like carbon 12 or C12. And it's always going to be the mass number, because if we have the symbol or if we have the name, we could figure out what the atomic number is. So we don't need to give that information. That would be redundant. We would also be able to look up, or you could be given the natural abundance, the natural percent abundance, which lets us do some fun problems. I like natural abundance problems. I think they're clever and fun sometimes. Questions so far about our particles? Subatomic particles. We're covering a lot of ground. A lot of this should be reviewed from Chem 20. All right, what are the atomic number, mass number, and symbol for the carbon isotope with 7 neutrons? And how many protons and neutrons are present in an atom of 39 over 19K? There's a little periodic table there provided for you. So I'll give you some time to do this, to give your brain some rest or time to catch up, and also let you practice a little bit. All right, for A, we're looking for the atomic number for carbon with 7 neutrons. What is the atomic number? The atomic number is 6. It's the number of protons. That's the number of protons. The mass number is what? 13. It's 6 plus 7, the number of protons, plus the number of neutrons. So it's 13. And what would be the symbol? C. So we could write it as 13 over 6C, C13, carbon 13. How many protons are present in an atom of this symbol? 19 protons. Because that lower number is 19, and that's the number of protons. It's the atomic number. And then the bigger number is our protons plus neutrons. So how many neutrons do we have? 20. We do 39 minus 19 equals 20 neutrons. Because that mass number, that top number, is protons plus neutrons. So if we subtract protons, we're left with neutrons. There's a third subatomic particle. So we've talked about protons. If you change the number of protons, you're changing elements. If you change the number of neutrons, you're changing isotopes. If you change the number of electrons, our third subatomic particle, then you are changing ions. So the number of electrons in a neutral atom equals the number of protons in its nucleus. So in neutrally charged particles, the protons, number of protons equals the number of electrons. However, those can change. So if we change the number of electrons, so we're staying within the same element, we can lose or gain electrons, and those become charged particles, which we call ions. So ions are charged particles. They can be negatively charged, they can be positively charged. So for example, sodium can become the sodium ion by losing 1 electron. Fluorine can gain 1 electron to become the fluoride ion. We've got 2 options of charged particles. One is positively charged, the other negatively charged. Our positively charged ions we call cations. So cations are positively charged. I wrote what I meant to. Cations positively charged because cats have paws. So that's one way you could remember that. And then anions are negatively charged. I don't have a fun thing for that one. So some words to memorize for us. Our ion charge is written as a superscript. So it's slightly raised with the magnitude the number first, followed by the sign, positive or negative. If it's just a 1 charge, we usually just leave off the 1, the 1's implied. That's a common theme, you may remember. Questions about ions? We'll be talking about them more. This is just like our crash course on ions. All right. At some point in history, 1869, apparently, Russian chemistry professor Dmitry Mendeleev noticed that certain groups of elements had similar properties. And so he found that when the elements are listed in order of increasing mass, the similar properties among different groups of elements occurred in periodic or repeating patterns. So periodic just describes something that happens on a regular basis, like the pendulum on a clock swinging back and forth is periodic, swings back every second or two. And so Mendeleev, I'm not sure how it's pronounced, observed and summarized as the periodic law. So the periodic law says that if we arrange our elements in order of increasing mass, which also correlates to order of increasing atomic number, then certain sets of properties recur or occur again periodically. So rather than just listing out our elements in this flat block and then another row below it, we can arrange our periodic table in a way that conveys more information, or that shows us more information. And that's where we get the periodic table that we have now. So Mendeleev organized the known elements into rows so that similar properties fell in vertical columns. So it would have looked something like this, which is a lot more similar to what we currently have for our periodic table. So groups/columns of elements typically, we'll just say they have similarities, similar properties. You could also call them families of elements. Family, of course, being the most powerful force in existence in the Fast and Furious universe, at least. So here's our periodic table with color codes for when these things were discovered. Some of them very recent, although some of these later ones weren't even named officially until like 2019, which is fun. You don't need to know when they were discovered. This is kind of just like a, hey, in case you're interested, here's when these things were discovered. So you can imagine, like, from this before 1800 or this 1800 to 1849, right, we've got a lot of elements in there, but we also would have a lot that would be missing. And so we wouldn't necessarily have enough information to be able to come up with a really good comprehensive periodic table if we're missing all of these elements that I scribbled over in red. Of course, we know about them now. And now we've got an ancient meme for you. And this is how, in 1869, Dmitry Mendeleev completed the first periodic table. It's a Tetris joke. It also doesn't really work because then like they would all disappear, clearing rows and whatnot. So our modern periodic table, we arrange things in order of increasing atomic number. The atomic number is the focus now instead of increasing relative mass, although they sort of go hand in hand. It also has a lot more elements because we've discovered now 118 elements. So here's the breakdown. There's a lot of different ways that you can cut the periodic table. One of the major ways that we can cut it is into 3 categories. Our biggest category, everything that's over in this yellowish color, all this stuff, these are all metals. And this includes a lot of things that we would call metals, so like Fe, iron, Ni, nickel, Cu, copper, Zn, zinc, Ag, silver, Au, gold. So lots of things, especially in the middle section, that we would know as metals, that we would instinctively, I hope, call metals. We've also got another large section up in the top right. These are our nonmetals, things that are not metals. They don't display the same properties as metals. And then we've got our weirdos kind of crunched in between, and these are our metalloids or semimetals. So these display mixed properties. They've got some of the properties of metals, but they also do some weird stuff. So generally you should know metals left side and left bottom side, nonmetals kind of in that top right corner, and then just somewhere in the middle, the metalloids. So our metals do things that we know metals do well, even if we don't think about them. So they're good conductors, meaning they transfer electricity really well, they transfer heat really well. They're oftentimes malleable and ductile, ductile meaning that you can make them into wires. And we do that especially because they're good conductors. Many of them are shiny, or they can be shiny. And perhaps most importantly, they tend to lose electrons when they undergo chemical changes. So metals, we'll write this down lower. Metals, because they lose electrons, form positive charge ions, generally. Our nonmetals have the same properties as metals. They're generally poor conductors. They're not ductile. You can't draw them out into wires. They're not malleable. They tend to be relatively brittle, and they'll just break instead of bending nicely. And these tend to gain electrons when they undergo chemical changes. So our nonmetals are going to form negative charge ions. And then our metalloids are not really that consistent. They exhibit mixed properties. You can also call them semiconductors because you can change their electrical conductivity. So it depends a little bit on temperature. So silicon is a very important semiconductor. Or metalloid. If you're only going to remember one, remember silicon. That's the reason that silicon is used in electronics. Like all electronics have silicon in it. We can also break down our periodic table into different groups. So we're excluding our lanthanides and our actinides, the two rows that typically show up below the periodic table. We're excluding those for this discussion. We've got main group elements in our first two columns and main group elements in our last 6 columns. And we've got 2 different types of group numbering. We've got A, and that A is for main group. It starts with group 1 all the way on the left, then goes to 2 or 2A, and then 3A picks up with the 13th column and continues on to 8A or 18. That A designation is sometimes helpful. A lot of the time, though, you're more likely to just see 1 through 18 for your group numbers. So those are our main groups, and then our transition elements or our transition metals are in the middle. So two major groups, main group and transition. I usually just call them transition metals. You should know these two distinctions. We also have named groups. So some of those groups, 1, 2, 7, and 8A, or 1, 2, 17, and 18 have names. More than that have names, but those are the most important ones. The noble gases, group 8A or 18, are mostly unreactive or what we would call inert. They don't react with things. They just generally don't participate in reactions. You can get them to participate in reactions, but they're very unstable if you're able to get them to participate in a reaction. They really want to go back to being their noble gas self. Our alkali metals, our group 1A or group 1, are all very reactive nonmetals. Sorry, metals. Very reactive metals. And these are our alkali metals. Group 2A, or 2, is our alkaline earth metals. What's bigger, 1 or 2? 2. What's longer, alkali or alkaline earth? Alkaline earth is longer. The longer name goes with the bigger number. I'm mentioning this because it's easy to get them confused. As long as you remember the names, the short one goes with the lower number, the longer one goes with the bigger number. So that's our 1 and 2. That's our main group elements over on the left side of the periodic table. And then we've got our very reactive nonmetals, the halogens. Like the lamp, halogen lamps. There's also some other fun ones that you don't need to know. 6A is chalcogens. I don't remember exactly what the base of that comes from. And then 5A is pnictogens, which starts with a P, as you might have guessed. Those are suffocating gases. It's like if you were in a room that was all nitrogen, you wouldn't realize that there wasn't any oxygen, you would just suffocate. That's the group that starts with nitrogen. So those are just for fun names. I think they're cool. All right, so our main group metals, they're metals. Metals tend to lose electrons, meaning they form cations. We already talked about this. I'll underline these because they're important. And it's the same number of electrons as the nearest noble gas. And just like emergency exits on an airplane, the nearest noble gas may be behind you. So you might have to wrap back to the previous row, and for metals, that's typically what we do. And so for our main group elements that form cations with predictable charges, the charge is equal to the group number. So 1A, our alkali metals, form 1+ charge ions. 2A, our alkaline earth metals, form 2+ charge ions. For example, 3A, what charge would they form? What charge would they form? 3+. So that's one of the reasons that these A designation group numbers can be nice. For our nonmetals, so our nonmetals being in this upper right-hand corner of the periodic table, those tend to gain electrons. So nonmetals tend to gain electrons, meaning that they form anions, negatively charged ions. And these have the same number of electrons as the nearest noble gas. So, for example, fluorine, we've got here on the periodic table. The nearest noble gas is neon. How many electrons does neon have? It's the same as the number of protons. So neon would have 10 electrons. So fluorine, when it forms an ion, is going to have 10 electrons. It normally has 9 electrons. It has 9 protons. If it has 10, then it has 1 extra electron, 1 extra negative charge. So it forms a 1 minus charge. And I think I'll get to show you this at some point. So the calculation that you can do for that A designation is that it's the group number minus 8. So for fluorine, fluorine is group 7A. So 7 minus 8 equals 1 minus charge. So it would be F minus. You can also just look at like how many places do you move over. Fluorine to the noble gases, you move over 1 place, 1 negative charge. Oxygen, you move over 2 places, 2 negative charge. Nitrogen, you move over 3 places, 3 negative charge. Hopefully I'll review. Here's more on that. The oxygen family nonmetals, the chalcogens, tend to gain 2 electrons and form 2 minus ions. So here are elements that form ions, main group elements that form ions with predictable charges. You will be expected to know all of these. They all follow that same rule. 1A forms 1 plus charges, 2A forms 2 plus charges, 3A or 13, 3 plus charges. And then when we move to our nonmetals, 7A moves over 1 to be a noble gas, 1 negative charge. 6A, 2 spots over, 2 negative charge. 5A, 3 places, 3 negative charge. So these are must know. Fortunately, we can figure them all out from the periodic table. Right, so as long as you have a periodic table and you've practiced these tricks, you should be able to figure them out pretty easily once you get the hang of, what group are these things in. You might not even need the periodic table. You'll just know oxygen's a 2 negative charge, nitrogen's a 3 negative charge, phosphorus also a 3 negative charge, magnesium 2 positive charge when they form ions. Here, let's draw in some arrows so that it stands out a little bit more, so you can find it later. All right, predict the charges of the monoatomic ions, meaning it's just one atom, ions formed by these main group elements. So N and Rb. Find them on the periodic table, figure out what charge they are. So nitrogen, we're going to find in group 5A or 15. So we can do that group number minus 8 to get the charge. -3, so this would be N3 minus. We could also count the number of spaces that we move over to get to the noble gases, also 3, so it's a 3 negative charge. Rb, they've got the meets. So Rb we find in our first group, our alkali metal group. So it's going to form a 1 positive charge. So Rb plus. So rubidium, when it forms an ion, will have the same number of electrons as krypton, the previous noble gas, the closest noble gas, which is 36. So it loses 1. These ones also work, you're just counting the other way. So how many places does it move over to get to where the noble gases would be if we shifted things over? Questions about ions? These are just some of the ions that you get to memorize. It's a good start. All right, atomic mass. I think I already mentioned Dalton was not correct. when he said that atoms of a given element have the same mass or atomic weight, different isotopes have different masses. We can calculate an average mass, which we would call the atomic mass. I know it says this like right below what I'm writing. The atomic mass is found below the symbol on a periodic table. Writing it makes it easier to find. So for example, for neon that we've got in class, this 20.18 that's in the bottom left corner of the cell, that's the average atomic mass. So for all the isotopes that are out and naturally abundant, on average, the mass of neon is 20.18. So there's some isotopes that are 20, there's some that are 21, some that are 22. We do a weighted average to calculate what that atomic mass is. Naturally occurring chlorine consists of 75.77% chlorine 35 atoms. You will be given natural abundance percentages if you need them, unless you're asked to find one. You don't have to memorize any of the AMU masses or percentages. So it's mostly chlorine 35 atoms, which have a mass of 34.97 AMUs. The rest of it is chlorine 37 atoms, which have a mass of 36.97 AMUs. And so we can calculate atomic mass. This is a weighted average. You can also use this to calculate your Canvas grades or predict your Canvas grades using a weighted average. I do this for calculating, predicting some of your like exam scores that you need for things. So convert the percent abundance to decimal form. So divide by 100. And then multiply by its isotopic mass. So 34.97 AMU, 0.7 brain's resetting. So the 75.77% gets converted to a decimal form. You multiply it by the AMUs. And then you add to that the same thing for the other isotope. And you would do this for however many isotopes you have. And then you add those together. You can also do it in one step. An unweighted average is what you hopefully know how to do. So if we had two things, 35 and 37, and they have equal value, then we do 35 plus 37 over 2. This is because they would both be 50%. 50% could also be written as 1 over 2. So if half of it is 35 and half of it is 37, then we can just combine those halves to make it the average that we know and love. But since they have different amounts, we have to take the amount, their fractional abundance, and multiply it by their atomic mass and add those up. All right, so we'll do an example. Magnesium has 3 naturally occurring isotopes. These have masses of 23.99 AMU, 24.99 AMU, and 25.98 AMU, and abundances of this, that, and the other thing. And then we have this very important word, respectively, which is not the same as respectfully. What does respectively mean? Anyone know? Yeah, they're in the same order. So we've got 2 lists, and they both go in the same order. So the first entry from each list goes together. The second entry from each list goes together. The third list from each list goes together. So isotope, we've got isotope 1, 2, and 3. Isotope 1 has, we'll do abundance first. Abundance, mass, and we'll call it weighted mass. I don't know if that's correct. So our abundance for our first isotope, 78.99%. To turn that into a decimal, we would just move the decimal place over 2 to the left, divide by 100. So 0.7899. That's 78.99% divided by 100. And its mass is 23.99 with units of AMU. So we're pairing up the first mass value and the first abundance. We're going to pair up the 24.99 and the 10%. So we'll fill in the mass for both of these other entries. And we need to convert this 10 to the decimal form. So we're going to divide by 100, 0.1 with 3 zeros, and 11.01%. We do the same thing. Questions? Mostly all we're doing so far is just laying it out in a way that it'll make it easy to calculate. And we're going to multiply our abundance and our mass to get the weighted mass, as I'm calling it here. This is where we get help from the calculator. So our first one, 18.949701 with units of AMU. Our second one is 2.499 AMU. Our third one is 2.860398 AMU. And then the last step is we add them all together. So we take all of those numbers and add them together, and we get 24.309099 AMU. I'll just round this to 4 significant figures. That should be about right. That should be correct, yeah. 24.31 AMU. There are a couple of signs. We're doing an average. There are a couple of signs that things could have gone wrong. One big tell, if we get a number for our final answer, this is an average. An average, we're always going to get a number that's between our biggest value, 25.98 AMU, and our smallest value, 23.99 AMU. If we got 23.4, that would be less than our smallest value. That cannot be correct. If we got a number that was like 26.5, that would also be a dead giveaway that we did something wrong and it's not correct. So our answer will always be between our smallest and biggest value. And in the case of having really skewed abundances, so like it's mostly this lowest mass one, our number that we get out should be close to this one because it's our biggest contributing factor. It's got the highest percent abundance, and that's what we see, 24.3. It's just a little bit over than the about 24 that we had to start with. Any questions about that? There's another type of question that's related to this. So you could be asked, you could be given two masses, the atomic mass value that we calculated here, and one of the abundances, and be asked to provide the other abundance. Or you could be given two abundances, a mass, and be asked for the other mass, for example. And those are more complicated problems. They're fun. So just be mindful that those questions exist and you might see them. Feel free to ask if you need help on those. And we'll stop there.